Good afternoon, everyone. Thank you for attending my talk. I am Seung-Hoon Han, and this is my second presentation at USENIX Security, so it's an honor for me. Today, I'm here to present our paper, Page-Oriented Programming, Subverting Control Flow Integrity of Commodity Operating System Kernels with Non-Writable Code Pages. Yeah, maybe this is the longest title in this session, so I have been repeating it every day for this conference. As the title suggests, we'll revisit the traditional page remapping attack with non-writable code and have discovered a novel way to bypass the practical and state-of-the-art kernel CFI implementations. This is our line. Memory corruption is attractive to attackers because it allows them to hijack control flows. To prevent these control flow hijacking attacks, control flow integrity, or CFI, was proposed. This diagram shows an example of CFI, and the lines represent a control flow graph, CFG. The main function calls the sort function twice using a function pointer, and subsequently, all functions verify labels before invoking function pointers or returning to the call site. If a function pointer is modified to point to a disallowed function like this, the malicious code is detected and blocked. While academic research has focused on and successfully reduced the size of the branch target set, practical implementations have concentrated on deployability and practicality. They integrate with compilation toolchains and utilize bitmap-based or function type-based verification methods with the static CFGs generated from the source code. They also adopt hardware-based CFI mechanisms such as Intel control flow enforcement technology, which restrict indirect branch targets to specific code positions. The combination of the hardware and software CFI is called hardware-assisted CFI. This table shows practical implementations for commodity OSs. Indirect branch tracking and shadow stack are features of Intel CT. And the last two, Clank CFI and FineIVT, have more strict CFI policies than others, so we targeted them. The original work emphasizes the importance of a non-writable code because if an attacker can modify the CFI enforcement code, it can be neutralized. Commodity OSs ensure it using CPU's address translation mechanisms such as page tables in the kernel and second-level address translation SRAT tables in the hypervisor. However, these non-writable code mechanisms only ensure non-writable pages, not the integrity of the code area. This slide shows the effectiveness of page-level non-writable code. On the left side, page tables protect CFI enforced code and read-only data with their own permissions like read, write, and execute. On the right side, SRAT tables protect the areas again with their own permissions, read, write, supervisor execute, and user execute. Even though the attacker can modify page tables in the kernel and set write permissions, code and credential modifications are prevented because SRAT tables still have the original permissions like this. So our target system is fortified with these hardware-assisted CFI policies and hypervisor-based page-level write protection. These mechanisms can hinder traditional attacks such as unauthorized code alterations, control flow hijackings, and even direct modifications to kernel credentials. However, we also assume that the system has an arbitrary kernel memory read and write vulnerability, so the attacker can modify page tables and leak kernel information with it. These attacker capabilities are not overestimated compared to previous studies. While developing a threat model, we had two questions about the protection mechanisms. One thing was, is page-level protection enough to ensure non-writable code? Because SRAT tables only ensure guest physical address to host physical address translations. The other was, is indirect branch tracking is enough to detect control flow deviations? Although the address of the direct branch target is fixed in the code, it applies only to the logical address space. Because of these two questions, we finally identified blind spots that can subvert the CFI enforced system we assumed before. If the page offsets of the kernel normal and kernel sensitive functions are identical like this, And if the attacker can modify the physical addresses of the kernel normal and function to those of the kernel-sensitive function, then the attacker can execute the kernel-sensitive using normal system call and arbitrary arguments like this. Now, we introduce a novel and page-level code reuse attack, page-oriented programming, POP. POP revisits page remapping attacks and exploits these weaknesses mentioned earlier. It programs page tables using a kernel memory read and write vulnerability, allowing for the creation of arbitrary control flows under CFI enforcement. This shows an attack scenario of POP. In benign cases, the normal system call executes sysnormal and kernel normal functions, not the kernel sensitive like this. However, POP is performed as shown in 3 stages: page carving, page stitching, and page flushing. Then now we can create a new control flow using page remapping and eliminate unessential sub-functions from the kernel sensitive. As I mentioned before, POP has 3 stages, and each one is also challenging, so let's see the core parts. The first stage, page carving, identifies system call candidates and gadgets. System call candidates consist of system call stubs, as shown in figure A. And figures B and C show core and of gadgets, as well as function type and partial type gadgets. Core gadgets link system call candidates to security-sensitive functions. No operation love gadgets unlink unessential functions from the candidates, gadgets, and security-sensitive functions. The second stage, page stitching, is a core part of POP and is responsible for 2 important jobs. First, chaining gadgets and data to create new control flows by remapping physical pages of gadgets to arbitrarily logical addresses with page tables. Figures A, B, and C show these types of page stitching methods: direct core chaining, indirect core chaining, and direct to indirect core chaining. Second, avoiding remapping explosion. Remapping functions necessitates remapping sub-functions and related data, which can result in remapping explosion. Therefore, as shown on the right side, unessential functions must be replaced with enough gadgets to mitigate it. The last stage, page flushing, wipes out stale mappings in the TLB to load new mappings. For page flushing, we use a simple approach. We remove global bits from the page table entries we targeted to lower their priorities and wait for a sufficient time until the TLB is flushed by other page table entries. Our evaluation system has CET-enabled CPU. It ran Ubuntu version 22.04 with LLVM version 6 and used the open source hypervisor Shadowbox. On this system, we targeted Clang kernel CFI and FineIBT across different kernel versions and configurations. For evaluation, we developed proof of concept exploit code with CVE 2013-2595. The vulnerability has page remapping capabilities, so it is suitable to evaluate our POP. We also analyzed the distributions of system call candidates and gadgets to show the feasibility. By using the CVE 2013-2595, we linked and identified these symbols from the kernel binary and memory to break kernel ASLR and identify kernel data structures and perform POP. If you want to know how we could do these or jobs, please check the source code in our paper. Well, before executing POP, the security-sensitive function, commit class over there, was connected to sys senuid function. And the commit class had 2 data dependencies and 7 sub-functions, as shown on the right side. After executing POP with the identified symbols, commit class function is connected directly to the sysRemoveX attribute function. And physical pages of all functions and data are remapped to their original positions plus 38A zeros. As shown on the bottom right, 3 unessential sub-functions are replaced with enough gadgets to prevent remapping explosion. So we finally able to escalate our privileges to root using the sysRemoveX attribute function. From now, I will explain the distributions of the candidates and gadgets. The candidates were identified on their prefixes, such as x64 and IA32s. Then we applied two rules to select them. First, system call candidates containing tail calls were excluded. Second, the first direct branch had to be reachable with an attacker-controlled arguments. By using these two rules, we identified over 220 candidates. Additionally, we found the characteristic that branch targets of the system call candidates were aligned by 16 bytes. So we list gadget counts in two categories. At the top, 16 byte aligned gadgets, and at the bottom, all gadgets including unaligned gadgets. In the case of function gadgets, over 10,000 core and knob gadgets were identified. So this is enough number. And for partial gadgets, we disassembled code units every 32 bytes across all page offsets. Then we found that most partial gadgets were unaligned gadgets, which means that system call candidates cannot directly use these unaligned partial gadgets. However, after analyzing the branch targets of aligned partial call gadgets, fortunately, we discovered that the targets of them were also unaligned. So this enabled us to utilize all unaligned gadgets with the aligned partial call gadgets. I mean, we could use them like bridges to unaligned gadgets. So if you want to know detailed information about these numbers, please check our paper. Yes. There are several potential mitigations against POP, as you know, such as page table protection and kernel compartmentalization and data flow integrity. But in our view, the redirection protection feature from Intel can provide a fundamental solution to prevent page remapping attacks like POP. This feature includes hypervisor-managed linear address translation, which translates guest logical address to guest physical address instead of page tables. And now I also think, unfortunately, this will also be scrutinized by many researchers here because of this presentation. All right, this is the conclusion. First, we analyzed blind spots that focus on page-level non-writable code and indirect branches. Second, we introduced a new page-level code reuse attack, page-oriented programming, and evaluated it to demonstrate its feasibility. And last, we proposed potential mitigations against POP. All right, this is the last slide of my talk. Okay, thank you for listening and your precious time.